Thank you. Thank you for the introduction. So yeah, today I'm going to talk about the art and craft of large-scale quantum error correction simulation, something that is really important for us at Quantique. And I hope that after this presentation, which I hope is accessible enough, you will have some tools to start the hackathon in the quantum error correction and compilation program. So as most of you may know, we want to build a quantum computer to achieve the so-called quantum advantages, a great speed up in many fields like chemistry, machine learning, and cryptography. And through the event today, QHack, I've seen many great presentations of other speakers that shows many applications of quantum computing. So you all know that there's a great potential if we can build a quantum computer. But we need, like I said, to achieve these great quantum advantages to build a quantum computer. And in fact, we need not only to build a computer, but a fault-tolerant one. So this is our goal at Quantique. We aim to get to fault-tolerant quantum computing as fast as we can because we believe this is where we will get the most impactful application. So what is our path is that we think about quantum error correction in all our design decisions, from how we build a qubit with the help of bottleneck code to how we connect them and how we scale to 1,000 or 100,000 or even million of qubits for large-scale application. So that's why today I've decided to give you a crash course on quantum error correction and fault tolerance with a little bit of flavor in how to perform actual simulation. In this presentation, there will be nothing new, stuff that you can find in books, like online and stuff like this, but I hope that it will be, like I said, useful for you in the hackathon and can give you a head start if you want to dive deeper in the field. So the basics for error correction, it starts with the so-called Pauli group. If you're a physicist, you mostly have heard of the Pauli group. So there are three operators, the X, the Z, and the Y. So the X operator is also called a bit flip, so it changes 0 to a 1 and a 1 to a 0. The Z operator is called the phase flip, so it has a +1 phase to the 0 and a -1 phase to the 1 state, and the Y operator is a combination of both, so a phase flip and a bit flip combined, up to a global complex phases that is not really important in quantum computing. One interesting property is that they all entry commute pairwise, so XZ, if you want to apply them in the reverse order, you need to add a -1 phases. And okay, so this is it. And now if we want to scale to a larger number of qubits, let's say n qubit, we will consider an extra operator, the identity, so doing nothing, and we can construct the n qubit Pauli group, which is just string of these operator of length n. So for example, the 2 qubit Pauli groups look like this. You have identity on 2 qubit, identity on the first X on the second, identity on the first Y on the second, so on, so on. There are like 16 operators like this for the 2 qubit Pauli group. And they have nice important property. First, they have eigenvalue ±1. They are a basis for arbitrary matrices, so any matrices can be written as a sum of Pauli operator. And they also each, the n qubit Pauli operator, they either pairwise commute or anti-commute. And how can we use this in practice, this Pauli group, to design the quantum error correction? That's the goal of this presentation. So it all starts with the Knill-Laflamme condition that mentioned that if we can correct a set of errors, we can correct any linear combination of these errors. So if we can correct for Pauli error, we can correct for all of their linear combination, which is a really large class of error. Or if I say it in the other direction, to correct many errors in quantum computing, it is sufficient to correct Pauli error, so Pauli operator affecting the code, the circuit randomly. So that's what we focus on. We focus on correcting Pauli error. As an example, the simplest quantum error correction code that I can think of, and I think many people, is the repetition code, the 3 qubit repetition code. So imagine I have 3 qubits represented by a blue circle here. I will add constraint on top on them to be sure that the state that they are in is satisfy a set of constraints that we call stabilizer. So in this example, I have 2 constraints. The first one is the Z1, Z2 constraint, and the second one is the Z2, Z3 operator. And what I mean by a constraint here is that at any given time, for the state to be valid, it needs to be a +1 eigenstate of these 2 operators at the same time. So if there's an error, for example, an X error on the first qubit, since X error anti-commute with Z1, Z2, the Z1, Z2 stabilizer will raise an alarm. It will say, I'm anti-commuting with the error, so the parity will now be -1 instead of +1. So it's kind of an alarm. So this will help us to detect the X1 error. Similarly, if there is an X error on the second qubit, so an X2 error, they will both raise an alarm at the same time because they both anti-commute with the X2 error. Finally, if we have an X3 error, the last stabilizer anti-commute with X3, only this one. So only this one will raise an alarm. So we have 4 different alarm patterns that we call a syndrome. And from one of these 4 patterns, we can recover which error affected the system. Of course, the repetition code is not the best code out there. In fact, it's like one of the worst. It's a really simple example, and it can correct only X error on single qubit or combination of these errors. But you may imagine that we can design much more sophisticated code with a larger syndrome pattern that can detect larger class of error. So how do we do this measurement? Like, how do we detect that there is an error? Well, it's quantum computing, so we use quantum circuit. So in my example, I have 3 qubits, so now I'm drawing 3 wires, 1 for each of those qubits, and I will add 2 extra wires, 2 extra qubits, 1 for each of the stabilizer that I want to measure. The top qubit will be the Z1, Z2 measurement, and the bottom qubit will be the Z2, Z3 measurement. So I initialize those 2 qubits in the 0 state, and in the end, I will measure them in the Z basis. What I do next, I want to have the Z1, Z2, so I will use CNOT gate, like this, from the first qubit to the first stabilizer, and then the middle qubit to the top stabilizer. So this will add the parity of Z1, Z2 to the stabilizer qubit, and I will do the same with another set of 2 CNOT on the last qubit to have the parity of Z2, Z3. And then when I will perform the measurement, the top qubit will measure Z1, Z2 as I mentioned, so +1 or -1 value. -1 is an alarm, and Z2, Z3 will be measured by the last qubit. And you can see this gives us a 6-step circuit, like 6 time step, that can perform this measurement. But of course, we want to have a better circuit than that. So in fact, I can compress everything into 4 time step, which is more efficient, in fact, 30% more efficient. And we want to do that as much as possible. A short circuit, they run faster because there are less things to do. And secondly, there's less time for error to accumulate and propagate and for fault to destroy the information. So the shorter, the better. So we usually want to do this. And basically, that's the kind of goal of error correction and fault tolerance. We want to build this circuit that will help us measure some alarm, some error syndrome, in order to be able to find a good correction, to detect the error and find good correction to correct them. Of course, this circuit, they can be quite large for more sophisticated code. So this raises the question, can we simulate this circuit and error correction, error detection, and all of that stuff? And the first thing that you may think is, yeah, but I thought that the quantum circuit, they are hard to simulate classically. And in fact, that's generally true. It's generally really hard to simulate a quantum circuit classically. And if this was false, there will be no quantum advantages. We could just build a really big classical computer and then simulate arbitrary quantum circuit. Of course, this is not the case. We cannot do that. And another question that you may ask, in fact, is noisy circuit, they should be even more difficult to simulate. So that doesn't seem too good to simulate error correction. Like intuitively, we may think that it's impossible to scale to large system. But by searching the literature a little bit, I'm just showing 2 figures here. The exact meaning of the figure is not really important. The thing that you should focus on is the thing that I've highlighted in blue. So on the left figure, you see that they go up to 22,500 qubits. And in the right figure, they go up to 10 to the 5 qubits, so 100,000 qubits, which is quite a big amount of qubits. And they are able to perform a numerical simulation using a classical computer. So there must be a trick, and this is what I'm going to present. And the trick is based on the Gottesman-Knill theorem. So the Gottesman-Knill theorem is a really important theorem in error correction, and it mentioned that we can simulate noisy Clifford circuit in polynomial time on a classical computer. So if you're less familiar with this wording, polynomial time means that we can do it efficiently in a reasonable amount of time. We're talking hours, day, maybe week, instead of a year, million of year, the age of the universe. So something that we can scale quite efficiently. And a Clifford circuit, they are made of a few basic building blocks. So the well-known Hadamard gate, also the S gate or the phase gate, then the C0 gate, and then also a preparation of Pauli basis states, so the 0 state, the 1 state, the plus state, and the minus state. And finally, measurement in the Pauli basis, so measurement in the Z, Y, or X basis. And any circuit that can be constructed from these building blocks is also a Clifford circuit. Before we move on, one important thing is that Clifford circuits are not universal for quantum computing. You cannot use them to perform any computation. No, you cannot do any computation, but you can still perform error correction to quite a large scale. And in fact, this is sufficient for error correction, but not universal quantum computing. The idea is the conjugation relation of the Clifford group. So imagine you have a Clifford gate, I call it C here, and a Pauli operator before. There exists another Pauli operator Q that you can apply after it, and it will give you an equivalent circuit. For example, if you have the Hadamard gate, you could have an X operation before the Hadamard gate. This is completely equivalent to a Z operator after the Hadamard gate. More relevant for the current example, if you have a C0 gate and an X error before the control, this is completely equivalent to having 2X error after the C0 gate. Similarly, if there is an X error before a target of a C0, this is completely equivalent to an X error directly after the target of the C0. So we can swap them and decommute in this case. And then we need to do an assumption to move on. This is not a necessary assumption, it's just helpful in this case. I will assume that without error, the outcome of each measurement is +1. You don't need to do that, but it simplifies the simulation quite a lot. And it's a fair assumption because everything +1 means that there's no error, everything is fine, no alarm. So this allows us to simplify the measurement quite a bit. And the only rule we need is that if there's a Pauli error before a measurement, if they are in the measurement is the same as the Pauli error, you measure +1. And if they are different, you measure -1. So how can we use that to simulate error propagation in a quantum circuit? Imagine that I have my Clifford circuit here to measure the repetition code, and I have an X error on the first qubit. I can straightly move it to the next step because there was nothing on this qubit for that time step. And now, if I look, I'm in front of a control of a C0 gate. So now I can replace it with 2 errors in the following step. And now if I look, the first error is in front of a target, and the second error is in front of nothing. So again, I can simply move it to the next step. Now, in the end, if I look, I have an X error before a Z measurement. So these are different. So I will measure -1 for the first qubit, +1 on the bottom qubit because there were no error, and I'm left with the X error. And this is exactly the error path, the alarm pattern that I should have for this X error on the first qubit. So this is the idea to simulate error propagation. And if we want to go a step further and say that the error and fault can happen also while we're trying to detect an error and correct them, you can imagine that I have the same circuit, but now this C0 here has a fault. How can you do a model for this? A simple one is just to sample randomly another Pauli error directly after the C0 gate. So for example, it could be a pair of X error that you have sampled randomly. And then it's the same idea of propagation. So the first X is in front of a control, so it propagates. So that's why we have 3 X's now. And now in front of each measurement, there's an X error. So in both cases, we will measure -1. And we're left over with this X error in the middle qubit with the good error detection pattern. Unfortunately, there's nothing that prevents that. There's also an error in the last time step in the middle qubit. And again, to represent this, I will need to sample a new Pauli operator. So for this example, I could say that randomly I've selected that there's a Z fault after waiting there. Even if I do nothing, there can be a fault. So now I am left with a Z and an X error on the middle qubit, but a Z and an X error is simply a single qubit Y error. And now this will be, I will have this error pattern with the Y error in the middle qubit. And basically, this is all there is to simulating large-scale error correction. We can use the Gottesman-Knill theorem to simulate a Pauli error propagation and sampling in Clifford circuit in polynomial time. And this is sufficient if we want to perform error correction simulation. These are the only two tricks that you need to use, and you can scale to 1,000 or million of qubits if you want to, and you will still be able to simulate like error propagation and detection and sampling in a quantum computer with a classical machine. So if this is something that you find interesting, that you would like to contribute to building software that allows to perform such large-scale simulation of fault-tolerant quantum computing, at Quantique, we're actively looking for a position in high-performance computing, so HPC expert. If you're interested in that position, please send me an email at maxime@quantique.ca. Thank you.
Thank you so much, Maxime. I've always heard about quantum error correction being something like solving puzzles, a very interesting field. And the way you explained it, it sounded definitely fun. Like how the error propagates, it was very, very clear. Thank you so much for that. I don't think I've ever seen an explanation that was as clear as your slide. So thank you for this crash course. And I hope everybody else enjoyed in the chat too. We do have questions, so I'm going to get started with the questions that we have. So our first question from QMath A&M. The error correction needs to be done after every gate applied to the original 3 qubits. Otherwise, it would only work when we know the expected result, right?
Yeah, so that's right. If we want to build to do computation with the computer, it's true that every time step, like imagine you want to do a teleportation, the circuit for teleportation, there's like a few gates, CNOT, Adamar, everything. After every time step, you should do error correction, or maybe every 2 or 3 time step, but you should not wait too long, else there will be too much error that will accumulate and you will lose the data. But if you need to do it like mentioned quite often in order to don't let the error accumulate too much in the system.
Awesome. Yeah, we saw how the error propagates, so you absolutely don't want to let it propagate and accumulate.
Yeah, exactly.
We have another question from Alejo Monbar. Can you tell us the extra number of qubits and depth required in any quantum algorithm you have used, using one of those error correction techniques, or at least an estimate?
So the largest simulation I've done, they use roughly 20,000 qubit, and the depth of the circuit was around 10. But this was just for error correction. So I've never performed a full calculation with them, and these are much harder to simulate when you start to want to do fault-tolerant quantum computing, and you have to take into account T-gate and stuff like this. They are much harder to simulate. But for fault-tolerant, like what I've shown so far, the largest one I've built are like 10 to 100,000 of qubit with like depth 10 to 20. These are the ballpark of what I have simulated so far.
Wow, that sounds huge. That sounds like a lot. So I guess also, like, for the people asking, it depends on what gates you're using, right? What circuit you're using. If you have a very random circuit, then you will need more extra qubits for a correction. If you know exactly what you're doing, maybe can you find error correction algorithms that require less extra qubits?
Yeah, of course, if your quantum computer is doing only one single thing, then you could optimize everything to be as efficient as possible to do that single thing. But that's not the goal. We want to do a general purpose quantum computer. So who know what in 10 years or 20 years or in 50 years the people will be running on these computers. So we have to be agnostic of what will be run, and we need to be as general as possible and hope to correct as much error as we can. Like we cannot, yes, for like NISQ application, near-term application, there is some value in like having really specific implementation, trying to remove as much as and be efficient as possible, remove extra qubit. But in the long term, I think we should err on the safe side and afraid to add a few extra qubit to be sure that we're more robust. And don't forget that we talk about 10,000, 100,000 qubit here. So like the qubit budget is maybe more generous. Like having a factor of 2 in this order of magnitude is maybe not as bad as going from 10 to 20 qubit, which is maybe a bigger step than from 1,000 to 2,000 or something like this, where we can expect that we already know a little bit how to scale like quantum computing at this point.
That's right. We will be remember the days when we were worried about simulating 20 qubits. So thank you so much. Great questions. We'll still have more questions. So make sure to go to the Discord. Maxime will be there answering the other questions that we couldn't answer here. And we do have a giveaway. So Maxime, we will have to say goodbye to you. But for everybody else who asks questions, we will have a giveaway. So thank you so much, Maxime.
Yeah, bye-bye. Goodbye.